So by the end of today's lecture, you'll be able to explain the concepts of a pure substance, what's a pure substance, and what's a phase change, and what are the phases that a pure substance can go through. And also you'll be able to understand the PVT surface. We'll get into that real quick, like what is PVT surface, and then what are PV, TV, and PT diagrams, and how we can interpret these diagrams. So that is a very important aspect. In the quiz one also, you will be tested on this one. So the important points and all these things, which we will be discussing in the coming slides real quick. And also, the most important one, use thermodynamic tables to find properties. So whenever you find a thermodynamic equation, sometimes like for real substances, we don't have any equation to calculate the properties sometimes. In that case, we have to go into property tables and check what is the properties at this given state. So it's very important you learn this one carefully. So if you want additional reading, you can read from chapter 2.1 to 2.7 in your recommended text, as mentioned earlier. Okay, so what is a pure substance? Let's go through the definition. Pure substance is a substance that has a homogeneous and invariable chemical composition. Okay, so homogeneous means like if you check from any point, it should have a similar composition, right? And the chemical composition should not be varying with time or with the points you are checking, right? There are some examples given here for pure substance: water, water vapor, ice, CO2. Like you can assume that if you take a glass of water, then it's going to be a pure substance. And if you take steam, then it's going to be pure substance. Like if you take an ice cube, it's again a pure substance, right? And if we take a mixture of liquid water and water vapor, still it's going to be a pure substance. Yes, it is, because if we try to fit this into our definition, then you can see in a water, liquid, and vapor mixture. So when we go across the mixture, we don't have a chemical variation, like chemical composition of the mixture does not change. The proportions, they stay the same. So that is one important notion. So whether a substance being pure or not does not depend on the phase of a substance. If it can have a phase mixture, or it can have liquid, solid, or vapor. And then we have another example, air, right? So air is a tricky one. So when we take a gas, we assume that every component in that gas is homogeneously mixed, right? So if we take that, if we consider that this entire box that I'm speaking out of is filled with air, let's assume this is a tank or something, and then when we have air, we check this block, and then the proportions that we have, it's not going to change from this point to this point, right? Because I don't remember the exact proportions. Let's say, for argument's sake, 70% nitrogen, 16% oxygen, and 10% CO2, something like that, right? So that whatever the ratio is, it's going to be maintained. So it's again considered to be a pure substance. So you can see that sometimes there could be a mixture, but if it is uniformly mixed and everything, so then we can call it a pure substance. But with air, there's a catch. Air is a pure substance as long as there's no phase change. Why is that? Can anybody guess why would that happen? Why air is a pure substance only in gaseous phase? Any ideas? Anybody? Okay, so because the atoms are separate. Yeah, like, so you are getting somewhere closer. So let me explain it again. So now with air, what happens is, like, we have nitrogen, oxygen, and all the other components, right? So when we are in the gaseous phase, everything is a gas, so the composition will be uniform. But if we keep cooling this thing, then if we keep cooling this one, let's say the freezing point of one substance is different from the other substance, right? So now all of a sudden, let's assume that nitrogen freezes first, right? And then nitrogen freezes and oxygen, CO2 and other things will be moving around in the space. Now if we think of the frozen component and the or like liquefied component and the other gaseous component, then the composition is not the same. So that's not going to be a pure substance. That's why there's a disclaimer: air is a pure substance as long as there's no phase change. Okay. Okay, now we come to a very interesting diagram, and it's very important that you understand this one very clearly, because sometimes students tend to like not get this one. Please pay attention and ask questions, and we'll take as much as time we need and get this clarified. Okay, so in previous lecture you remember that we discussed density of a substance depends on pressure and temperature, right? So, and we know that the specific volume is the inverse of density. So basically we can write specific volume to be V equals 1 over density, right? So that way you understand that if density is something, then density is a function of something, then again the specific volume is going to be a function of the same variables. So we can say that specific volume is a function of pressure and temperature, or in other words, specific volume depends on pressure and temperature, right? So in your high school you learned the equation PV equals mRT. Oops, I went across the space. PV equals mR, again there, sorry, my bad. PV equals mRT finally. So now in our high school we learned that PV is equal to mRT, right? And similarly we can say that P specific volume is equal to RT, right? So here you can see that if we take an equation for the specific volume, it's dependent on pressure and temperature, right? So, but it's very important to note, this is ideal gas equation. We cannot use ideal gas equation for liquids. As the name implies, it is for ideal gases. You may be laughing at your end like, okay, we know what's a gas and what's a liquid, and we are not going to use it for a liquid, right? But trust me, you'll be surprised to see how many students have applied this on water in the previous classes, right? So don't do the same mistake. Ideal gas law cannot be applied on liquids. And more importantly, ideal gas law is for ideal gases, right? Ideal, and not for real gases. If you can approximately make it closer, like assume the gas is closer to ideal behavior, then definitely we can say we can apply ideal gas equation under that assumption. But before doing that, you have to check whether this is close to ideal behavior. So how we determine that, we'll discuss later, right? So now we established one. We had a relationship that we already know to determine the relationship between the specific volume, pressure, and temperature, right? But still, we cannot use it for real substances. We can use that relationship only for ideal gases. Now at this point, you'll be thinking, you should be thinking, okay, now we cannot use the ideal gas law that we know. Now what are we going to do, right? So now let's try to find an answer for your question there. So that's why people develop the PVD surface. We don't have an equation or a model that can mimic the performance of liquids, solids, liquid solid vapor mixtures and everything, right? So to answer that, people develop the PVD surface. What is this PVD surface? It carries the empirical values or experimental results on what's happening at given state, at a given state. So if we know pressure and temperature, people measured what's the specific volume at that given point. So this surface that you see here, the surface that you see here contains that information. So instead of going for an equation, it has all the information related to PV and temperature relationship and gives that information. Before moving forward, it's very important that we understand this is a surface. It's true that it's a 3D surface, but still it is a surface, right? So if it is a surface, I believe like you have drawn 3D plots in Excel, MATLAB, or wherever. And if you have not drawn it, but still you might have seen 3D surfaces, right? So when you see that it's a surface, you get the point, right? And there, when it is a 3D surface, what can we say about this statement? If I select a given temperature like this, okay, and then given volume, let's say this is a constant volume line, and we have a point here, okay. Now, what can you say about this point? Can we have, for this state, can we have two different temperature values, few different temperature values, or one temperature value? Can you answer that in the chat? Okay, we have one answer as one, and any others? Okay, so the answer is one, and I'm happy to say that you are getting it right. So it's correct. Thank you everyone for answering. And you can see it's one layer, right? So if it is a surface, so you have nothing above or below this one. So that way we can assure, okay, this is the state. So it is similar to having an equation, but we just have a figure, right? Now let's try to go through this one and see what are the information that is given here. So this PVD surface have single phase region, right? Some single phase regions. What is single phase? So in this phase, if it's either solid, liquid, or vapor, gas, or something, right? No two things are in equilibrium. So we have solids here, right? And we have vapor here, and then we have liquid here, and then we have gases here, gas here. So this is for given substance, right? So for every substance, if we take water, then you will have a PVT surface. If we take CO2, then you will have a PVT surface, right? So for any substance, you will have a PVT surface. Now let's try to see. Okay, now we identified four single phase regions. Wait, so did we say liquid, solid, and vapor earlier, and now we have gas? Aren't you confused? So like, what is the difference between vapor and gas? Any ideas? By just looking at it, can you see a difference? Okay, let me answer that one for you. So vapor and gas, there's obviously a difference. The difference is with vapor, at a given temperature, if you apply more pressure, at some point you see liquid with vapor, right? So if you take, let's say, if you take some water vapor and we press it, and then at some point we'll see water. But if it is a gas, then no matter how much you compress it, you cannot get the phase to change. So it will remain a gas. So you apply more pressure, doesn't matter. High pressure gas will be there. So it would not turn into liquid. So any questions of the points that we discussed so far? Okay, I see none. And I believe now you are clear with the single phase regions that we see on this PVT surface. Okay. And in addition to this, we have two phase regions. So what are two phase regions here? Solid liquid phase, that is here. And then we have solid, I'll use another color. We have solid vapor region here, right? And we have liquid vapor region here. Okay, so can we think of examples for these ones? Solid liquid region, right? When you are driving close to a lake, you see that sometimes in a winter, sometimes ice is like floating on the water surface, right? So how to know if it is single or two phases from the graph? So like this is, I mean, these are developed experimentally. So like once we have the graph, then people know what they observed. So they have recorded this information here. That's how we know. Did I answer you, Menna? Awesome. So for solid liquid thing, so I was telling an example. So when you're driving close to a lake, you see that ice is floating on the water surface, right? So there you have solid and liquid in equilibrium, right? So because nobody is creating ice artificially, but it is there like that. If you drive in the morning and if when you are coming back in the evening, then still you'll see the ice is there, right? Because they are in equilibrium, right? When the temperature changes, then it will vanish. And then we'll try to think of an example for liquid vapor. So I'm pretty sure that you have seen this equilibrium quite often, right? So when you turn on your kettle and like you heat up water or coffee or something, and then you see there's vapor up there, and then at the same time there's liquid. So liquid and vapor in balance, right? So this is an example for liquid vapor region. So, and that is a region that we'll be working on quite intensively. In this course, liquid vapor region is a very important one. And then solid vapor. To be honest, I could not think of a solid vapor equilibrium in the sense of water. Maybe like in a snowy day, like we have some moisture, so that is a solid vapor example. And also like a quite visible one would be the case that we use dry ice. So liquid nitrogen, when we have the solid nitrogen and we put it there and we have some gas coming up, so it's kind of example that I could think of. Okay, so any questions about two phase regions? Okay, so now we have identified this is like there are two phase regions and there are single phase regions, right? And then there's another important line on this PVT surface. It's triple line. right? It's triple line. So now, what is the importance of this line? So you see many lines, right? So you see isothermal lines all along, but this isothermal line has some different importance. If you look above and below the triple line, you can see in this side, let's say side 1, we have solid and vapor, and side 2, we have liquid and vapor. And when we go to the end of the triple line, like here, we have solid and liquid, right? So you can see in any given point, we have solid, liquid, and vapor in equilibrium on this triple line, because like the boundaries are containing solid, liquid, and vapor, right? So if you see, to give you an idea what this means, if you see ice, water, and water vapor at a given point, that will be on triple line. That state should be on triple line. But like there are many conditions, like many specific volume values that you can get into this triple line, right? So another important thing to note here, like when we look from this end, we just have one temperature and pressure value for the triple line. The volume can change, as you can see, the specific volume can change, but there's only one temperature and pressure value. So when we look from this angle and create a PT surface or PT diagram, would you see a line or a dot in that PT diagram? Can you answer in the chat? The triple line, would it be a line or a dot? Perfect. You guys are nailing it. So it's going to be a dot, right? So you can see it here. So on a PT diagram, we call it the triple point instead of triple line, because in a PT diagram, we don't see the line, right? Does a triple line only exist for isothermal conditions? So isothermal means the temperature does not. So usually we use isothermal, the word isothermal, to explain processes, right? Isothermal process. But what we are discussing right now is not a process exactly, but states. So for an example, this point is going to be on triple line, right? So we cannot say it's isothermal or whatsoever, but we have only one temperature and pressure value for triple line. Am I making sense, Domi? Did I answer your question? Okay, perfect. Now we understood what is triple line, right? In addition to triple line, there's another important point that we need to know. Triple line and triple point we already know, and there's one more thing that is called the critical point, right? What is a critical point? To understand this critical point, how do we find it? Okay, we need to see that there's a line, there's a boundary line here to the dome, right? So what does that do? Like it separates, this is the liquid region, right? It separates the liquid region with liquid and vapor region, right? This is the separation line, the red one. So we call this saturated liquid line, right? Saturated liquid line. Now similarly, in the other side we have this line, Let me pick another color. Yeah, right. We can call it saturated vapor line. What does it do? Similar to the saturated liquid line, it separates the liquid plus vapor region from the vapor region, right? So this region is vapor region and this is liquid plus vapor region. So this is saturated vapor line, right? Now, at the critical point, these two lines meet each other. At critical point, these two lines meet each other. Okay. So by observing that, we can define the critical point as the point where the saturated liquid and saturated vapor lines meet. Okay. And when we try to see beyond that, like that observation, you can see that above critical point, this region. Okay. Let me get rid of some of the information here. Above critical point, this region is gas. Okay. So now, what does that mean? So beyond this critical temperature, the substance will remain a gas, despite of the pressure that we apply. Okay. All right. So that's what we have to discuss about this surface. And did we get it crystal clear, or do we have any questions on that one? Any questions so far, or everything is crystal clear? Perfect. So now you can see when it is a 3D plot, it's very hard to comprehend, right? So like in a calculation point of view, in a manual calculation, if you had to go through like multiple axes and like find the point from this kind of a graph, then it's going to be a challenging task. Even in a computational kind of an exercise, if you want to write a code or something, if you want to interpret, like find the points from a 3D graph, you need to do more calculations compared to using a 2D graph. Okay, so due to this reason, people decided, okay, it's true that we have the PVD surface. So to interpret this one, we'll get the projections from this end and this end and this end, right? So if you look from angle 1, you will get the PV diagrams, right? So if you look from the angle 2, you will get a PT diagram, which is already drawn here, pressure temperature diagram, right? And then you look from top here, and then you get VT or TV diagrams. Are we making sense here? The 2D projections? Perfect. So that's how we come up with the famous PV, TV, and PT diagrams that we are going to use extensively throughout this course. So when we try to draw a process, it will be hard to draw it on a 3D surface, right? So we get the 2D projection, and then we use those projections to mark our processes and determine the work and energy balances and all these things. We use the 2D projections. And in addition to these 2D projections, like there's another cool source that you can check. The 3D model, I added the link here. I don't know the name of the author, but like maybe sketchfab.com is who did it. And there they have this PVT surface as a 3D model. So there you can go and like rotate it and see for yourself, right? So it will reconfirm you that this is just a surface. The other solid parts or the depth of the thing is not relevant. I mean, with these parts, like we have no use for these. It has no value for us because we are only interested in the surface, right? Okay. Now we are clear with what is the PVT surface. Now let's move on to the other projections. Now let's start with PT diagram. Okay, so as the figure shows, when we look from this angle, then we can get the PT diagram. Okay, so when we observe the PT diagram, it separates the solids and liquid using one line. So the line you see here, that the line that I just marked in dark blue, it is this region. Okay, so when we look from that angle, like it's like this, my hand has a width, right? But when I look from this line, this angle, like it's like a line, right? So that's what we see here. So we have a line separating solid and liquid regions. Okay, and then if you try to find a definition that matches this one, we call this line fusion line. Fusion line is what? The line separating the solid and liquid phases, right? So which essentially means the freezing temperature. Okay, and then we have another line here, right? So what is that one? The line separating liquid and vapor regions. Let me use another color for that one. Line separating the liquid and vapor region. So do we have a definition here in this one? So here you can see there's a definition, vaporization line. Vaporization line, what's the definition? The line that's separating the liquid and vapor phases. Okay, so liquid phase is this one and vapor phase is this one, right? You can see that liquid and vapor line that represents, oops, sorry, it represents this region, this two-phase region, right? Okay, and then there's another line. This line does what? It separates solid and vapor regions. It separates solid and vapor region. So we call that sublimation line. And then we have our friendly triple point, right? We have our triple point. We discussed already, right? And in addition to that, we have a critical point, right? So now if we look at this one, like there are a few things that we can understand, right? The first one, according to this graph, the PT diagram, if we know the temperature, let's say I know temperature here, right? And can we say the pressure at this point? Can we say? Anybody? Any idea? Can we say the pressure if we know the temperature at this point and we know that it's a two-phase mixture, right? So if somebody tells us this is a two-phase mixture, liquid and vapor, and this is the temperature, and what we can do is we go to the point that we intersect the vaporization line, and then we go back and find what's the applicable pressure. And usually in ideal gas law, if you have PVT surface, what we can say, how many parameters we need to know the state. Let's say ideal gas law. Let's speak ideal gas law. PV equals mRT. So to know all these parameters, how many parameters do we have to know? So like we can say that this is P specific volume RT. Okay. So how many parameters do we have to know? 2, right? Because R is a constant, it is already known. We either have to know PV or TV or TP, something, any combination does work there, right? But in this case, when we come back to our PT diagram, okay, now we know that this is temperature 1, T1, let's say, and we know T1, we know P1. Can we define this state? We cannot use ideal gas equation here, right? So we discussed that part already. I just took the ideal gas law to give you a sense. Like out of PVT, if we knew 2, there we could know the other one, right? So in this case, can we do the same? Can we know it? Any guesses? Any ideas? We have one answer saying yes. Okay, so let me answer that question. Okay, so now let's say this is the pressure and temperature, right? And you remember I told you that in this point, the pressure and temperature does not change along this line. So if we know the pressure and temperature, we can only locate this line. But we cannot pick a point, right? So there we have a catch. We need to know the specific volume and temperature. We need to know specific volume and pressure. Like down in the road, you'll know more parameters similar to this: enthalpy, entropy, internal energy. Like they can be used instead of specific volume to know that state. But for now, according out of these 3 parameters, you have to know pressure volume or temperature volume. Knowing pressure and temperature cannot define the state. Am I clear? Any questions? Any ambiguities? Okay, so everybody is getting it crystal clear. So to define the state in the middle of the dome, like the liquid vapor region, knowing pressure and temperature doesn't make it possible. It's not enough, right? So if we know the pressure, another important thing to note, if we know the pressure on vaporization line, if we know the pressure in a two-phase region, then we can tell the temperature. If we know the temperature, we can tell the pressure. Do we get that idea as well? Perfect. Now, okay, thank you very much for being engaged, and like please engage in some manner, like chat or use your mic or something, because it's very hard to teach to a monitor like without the feedback, right? So I hope you understand. Thank you very much for being engaged. Okay, now triple point data, right? So if we have a triple point, like for a given substance, it's going to be one temperature and one pressure, and it does not change for a given substance. Like for hydrogen, we know this number. For oxygen, we know this number, right? If we go back here, this is the triple point, right? For triple point, you cannot have multiple values for a given substance. For different substances, definitely you can have multiple values. And if you want to like say like you are the only one for your partner, you can say that if you are my triple point temperature, I'm triple point pressure. So one and only, right? So once you go along, it does not change. So keep that in mind. For a given substance, the temperature and pressure comes as a couple. Okay. And if you want to find the triple point data, then you can go to Canvas modules, and under important documents, you'll see table A, and from that you can grab the triple point data as needed. Okay. All right. So now we come to TV diagrams. Okay. So when you look from above, when you look at the PVT service from above, you can draw the TV diagram, right? So let's try to interpret a process. So now you have a piston cylinder mechanism, and it's important to note that piston is not constrained. It's free to move, right? So we start at state one. We just have liquid. So the liquids are out of the saturation liquid line, right? So this is saturation liquid line, saturated liquid line. And now our data point, our point should be out of here, right? So somewhere in this domain, point one. Are we clear about that one? So how we located that? So we have the pressure and temperature, so we can pick the point there. Okay. And then we heat it up so that the liquid becomes saturated liquid, right? Still no vapor involved, but it is saturated liquid. Where should the saturated liquid go? The saturated liquid should be on the saturated liquid line. So as the name implies, on that line we have saturated liquids. So what is the difference of a normal liquid and the saturated liquid? So in a saturated liquid, if you receive a little more energy, or if you expand it a little bit, then it will generate vapor, right? It's almost in the verge of like generating vapor or not generating, like on the line, right? So state 2 is going to be on saturated liquid line. And from 1 to 2, the path that we are going from 1 to 2, what can we say about the pressure? What can we say about the pressure? Does it change from 1 to 2? Any ideas? It does not change from 1 to 2. Perfect. You guys are getting it perfectly clear, right? So as the piston is not resisting, anyways, it's not going to get any pressure build up, because if we, like for an example, if I try to like push my hand using my other hand, and if it does not resist, then could a pressure build up here, because like I'm just like doing this, and it should be the same pressure as I initially applied, right? If I use the same force in this hand, and it cannot build a more higher pressure. But if I resist, if I resist from this hand, and I still try to force with more power or more force, and then there's a pressure build up, right? The pressure increases as I apply more force, right? So in this case, there's no resistance, therefore a pressure cannot build up. So it will remain the same pressure throughout the process from 1 to 2. So we go on a constant pressure line from 1 to 2. The process happens on a constant pressure line. So you see that the constant pressure lines are drawn here, right? Like this. So for given pressure, 10 megapascal, 1 megapascal, 0.1 megapascal. So for each pressure, we have constant pressure lines in a TV diagram, right? So now we have come to state 2. And from state 2, we still keep on heating to state 3. When we heat up the setup a little bit more, then we come to a point where we have liquid and vapor in equilibrium. Okay, so we come to a point we have liquid and vapor in equilibrium, and that point has to be on the same pressure line, right? The pressure did not change because we don't have any resistance. So we came on this line, and then we continue along this line, and state 3 is also on the same line, same pressure line, right? So then we again, like, don't stick to the numbers, I mean the pressure number, right? 1 atm, like I'm not looking whether it's the 1 atm line or whatnot. I'm just drawing it for explanation purpose, right? So from 3 to 4 we keep on heating. Now we provide more energy, right? Now with more energy, like, all the liquid in this chamber becomes vapor, right? So maybe you remember, if you have ever used a kettle, if you put water and you forgot to do anything, and then you come back and see, okay, there's no water inside, right? So this is what happened. So you provided more heat and more heat, more energy, and then you made all the liquid inside the kettle, you turned all the liquid inside the kettle into water vapor, right? Now we enter the saturated vapor line, state 4, right? What is saturated vapor line? It's like saturated liquid line. It's like right in the boundary where we had a bit of liquid and no liquid, right? Right in the boundary there. And now we keep on heating. So now the phase cannot change further because vapor is the best it can get. There's no other state, right? So if we keep on heating, maybe it can become a gas. So, but like in our investigations, we mostly are interested in the temperature range below that point. We are not going to go beyond critical point in our day-to-day devices, right? So now we continue on the same pressure line, and still we have the vapor. So are we all clear? Are we all clear about this one? Okay. Yes, Alan, you can ask your question. So if you apply force to a piston, it will become gas. No, if I apply force to the piston, what would happen is, essentially, before it moves, the pressure buildup will be higher. You know what I mean? So the initial pressure and everything will be different. So if we had a variable force, then it will keep on gathering, right? So let me take it from here. Like now, if you apply, let's say we have 10 kilograms on this one, then it will have more pressure. What's that? It won't be TV diagram because P will change. No. Like on TV diagram, also we can draw situations where pressure change. For an example, in this graph, if we draw a line like this, right? So interpreting this one will be a different story. But like if you draw a line like this, then definitely be a change in pressure as well. We can mark processes where the temperature, pressure, or specific volume changes on any graph if we have sufficient information. So Alan, if we add more weight on the piston, then it will change the pressure that it operates. Did I answer your question? No, pressure cannot make a vapor gas. No. Like if we keep on increasing the temperature, then it will become a gas, because when it exceeds the critical temperature, after critical temperature, irrespective of the pressure, it will be a gas. Are we clear? Okay. So let's move on. So by this point, you should be aware what is a saturated liquid line, and we already know what is a saturated liquid line is. And then saturated vapor line, we know that, right? Importantly, on saturated liquid line, there's only liquid, and on saturated vapor line, there's only vapor, right? And compressed or subcooled liquid. So compressed liquid or subcooled liquid, it's the same thing for the liquid region, right? So this region contains liquid. We already know that, right? Out of this, like left side of the saturated liquid line is going to be the liquid region. So we call it subcooled or compressed liquid. Okay. And then we have the superheated liquid region or vapor region here, right? So we call the vapor region as superheated vapor region. So it's just the names. So are we clear all about this? Any problems? We are clear? Perfect. So now the other one, we discussed about TV and PT diagrams, right? TV and PT diagrams. Now we add the last diagram from the PVT surface, PV diagram. So when you look at this one from this angle, you can get the PV diagram, right? So similar to the TV diagram, you have saturated liquid line here, and then you have saturated vapor line here, and then you have the critical point above here where the two lines meet, right? And inside the dome you have liquid plus vapor region. Outside the dome you have compressed liquid or subcooled liquid region, right? In the right side you have superheated vapor region. And it's almost the same idea. Like inside the dome, it's important to note, inside the dome in either TV or PV diagrams, pressure and temperature does not change. For a given pressure, the temperature will stay the same, right? For a given pressure, the temperature will stay the same. For a given temperature, pressure will stay the same, right? So in this one, I need to observe one more thing. In this graph, I want you to observe one more important fact. So you can see that this portion, this line is an isothermal line, right? Isothermal line. What can you say about this line? About the angle? What can you say? What do you observe? It is almost perpendicular to the specific volume axis, right? And it is almost parallel to the pressure axis. And if we are moving this way, now we are building up pressure, right? So that's what we are doing. When we are building up pressure, by looking at this line, what can we say about the specific volume? Does it change or not? It stays the same, right? So basically what it means is the change, the line might be slightly angled, there might be a slight change in the specific volume, but it is not significant, right? So as the pressure build up in the subcooled region, in the subcooled or compressed liquid region, as the pressure build up, the specific volume change is negligible, right? So if I draw another isothermal line, like this, let's say, it will look like this, right? Again, as the pressure build up, the specific volume change with a huge pressure gain is insignificant. So what can we say about, with this observation, what can we say about the specific volume at this point and on saturated line? V1, let's call it V1 and V2. V1, V2, specific volumes at 2 points. Are they equal or not? They are equal, right? This is very important. This observation is very important. So when you go to property tables, you'll note that for the compressed liquid region, we don't have the flexibility like P and T with the specific volume, like there's not many values given there, right? So in that case, we can assume the specific volume in a process going in the subcooled region or compressed liquid region is going to be similar to that of the saturated liquid, specific volume of the saturated liquid at that given pressure and temperature. So you neglect this pressure number, right? You stick to temperature and get the VF value from the tables on the saturated liquid line. Look for temperature. Temperature, not pressure. Are we clear on that one? Perfect. Okay. And okay, now up to this point, we covered some important theoretical aspects and we have a bit more theory to cover today. So before moving forward, let's all take a quick break and then let's all meet at 9:10. Hello everyone. Are we all back? Perfect. So let's start the class again. Now we discussed about the PVD servers, PV, TV, and PT diagrams up to this point, right? So now let's look into something very important, the quality and in the two-phase states, right? So you remember in TV and PV diagrams, we had a dome-shaped thing where we marked our saturation liquid line and saturated vapor line and critical point. And we said that inside this region, it is the liquid plus vapor region. So basically you have liquid and vapor as a mixture, as you see in this figure here, right? And now, if we know the temperature or pressure with specific volume, can we define a state inside the dome or two-phase region? We'll call this one two-phase region. There are other two-phase regions as well, but in this course, we are not going to consider other two-phase regions for our calculations. So we'll refer to this as two-phase region throughout the course series, lecture series, right? So inside the two-phase region, if we know the specific volume and either of temperature and pressure, can we mark a state? Any ideas? Definitely. Good, Alexandra. Like we can mark it because you remember from our T diagram, the pressure and temperature inside the dome is related to each other, right? So if we know the pressure, we know the temperature as well. So then if we only have pressure and temperature, we cannot mark the state, but either one of temperature or pressure with specific volume, then we can mark the state, right? So that's what we have done here. We have specific volume, and then we know the temperature inside this one because it does not change until the phase is fully changed, right? So this line will be staying horizontal altogether until all the vapor has all the liquid has become vapor. Then until this point, this line will be horizontal, right? Now, as we mark the point, as we see here, now we have a state. And we use another parameter called quality to define how much of a vapor mass do we have in the mixture compared to the total mass of the mixture. So let's say this is M vapor and this is the total mass of the substance is M. So what quality does is it gives us the ratio between these two masses, right? So you can see it here from the definition. We can see that. So in order to find the specific volume, we can use the specific volume definition, right? So specific volume definition is what? The total volume of the substance is divided by the mass of the substance, right? And then we can represent the total volume of the substance as volume of liquid plus volume of gas, volume of liquid plus volume of gas, and then we divide it by the total mass, right? And then the total volume of liquid, so mvap is the vapor mass. Did I answer your question, Mena? Okay, so now we have the total volume of the system in the sense of Vf and Vg. I mean the volume of the fluid and volume of the gas, volume of the liquid and volume of the gas. Okay, so now the specific volume of liquid inside this system is going to be equal to Vf, and specific volume of gas inside this system is going to be equal to Vg, right? So then in that case we can write the volume of the liquid portion as m liquid into Vf, because we can write V equals this, and then total volume equals m specific volume, right? And similar to that, we can write the total volume of gas is equal to m vap, the mass of the vapor, into the specific volume of the vapor. Are we clear up to that point? Any questions so far? Anybody? You can say if you are clear, you can say it's all good. Perfect. And now liquid mass of the system can be written as total mass minus the vapor mass, right? We can do that, right? Because this is only comprised of vapor and liquid. So if we subtract the vapor mass from the total mass, then we get the mass of the liquid, right? And then we divide the entire equation by m, as m is below. Then m divided by m becomes 1, and m vapor divided by m, according to the definition of x, it becomes x. And again we have m vapor divided by m, it becomes x, right? What's the point of adding m vap and m liquid into the equation? M vap and m liquid into the equation. It's just to come to the derivation that specific volume of a given state can be written by this. So we wanted to derive this equation. So as a step, we did that. Did I answer you, George? Perfect. So now you can see, if we want to present the specific volume of this given state, right? You see what I'm cycling or circling? So if we want to provide the specific volume of this given state, we can write it using equation 1 in top left hand corner, right? So we can use this equation to represent the specific volume of this state. So in certain questions, you will be provided with quality. It will say quality is 50% or 0.5, right? It can be a percentage, it can be 0.5. It's like a number, right? So the important note is that the quality of a given substance inside the two-phase region, can it exceed 1? Can X exceed 1? It cannot, because it's the vapor mass divided by the total mass, right? So vapor mass cannot exceed the total mass, therefore the X cannot go beyond 1. And can X go below 0? It cannot, right? Because if it is vapor mass in certain mixture, there will be no vapor. In that case, vapor mass is 0, and then 0 divided by m, it's going to be m. So we cannot get negative values for X. So we established that the X has to be between 0 and 1, right? And when we have an X value which is not equal to 0 and 1 inside the dome, like which is not equal to 0 and 1, let's say 0.5, 0.75, what can we say about this mixture? Do we have both liquid and vapor, or is it just vapor or liquid? If we have an x value which is higher than 0 and lesser than 1, then we can say, very good, Scott. So we can say it is a mixture of liquid and vapor, right? So in a question, if you see x is equal 0.5, x is equal 0.75, so what does that mean? So there you can clearly see that, okay, now this question is talking about something inside the dome, right? It's the first thing that has to come to your mind. Okay, and if I phrase the question in another way, so if I say, okay, this is a two-phase mixture or liquid plus vapor mixture, then definitely you know that x has to be greater than 0 and less than 1, right? So if it has both phases involved at the same time, then x cannot be something else, right? And we do not define x values, or we do not define quality for subcooled region or superheated vapor region. So x only belong inside the dome, right? X does not belong outside the dome. Are we clear on that one? Perfect. Now you remember in the previous slide we derived this equation, right? We derived this equation, and by rearranging this one to get an expression for x, you can write x as v minus vf over vg minus vf, right? So in certain questions the x will be given, in certain questions the specific volume will be given. So depending on what you get, you can calculate either the specific volume or x by interchangeably using these relationships, right? And there's another interesting parameter, not interesting here, actually it's boring, but useful. So it says vfg, it just give a value to vg minus vf. Vg minus vf is equal to vfg. So this number is given in the thermodynamic property tables, right? So this number is given in thermodynamic property tables. So in an exam situation, even though it's not very exciting, it's just boring, it avoids or it saves you one step. So if you do not use VFG, you will have VG and VF and subtract each other to find this number, right? So if we just directly got VFG from the graph or table, then you can straight away plug in VFG instead of this one. The same idea, you will get same answer, but you will save a bit of time. Are we clear there? Any questions so far? Okay, I see none. Right. So when you go into thermodynamic property tables, like you have property tables for each substance. For example, for water, for ammonia, and everything. So you cannot use property tables developed for water in a question where we use ammonia, right? Be very careful. Like if you are solving a question, please pick the right table, right? When we say right table, again, even if it is water, you have different tables for different regions, right? So for compressed liquid region, like you have B1.4, right? So for two-phase region, you have liquids in this region. right? B 1.1, 1.2, and so on. For superheated region, you have this table, right? So I'm not going to go into each and every table with you, like saying this is B 1.1, 1.2, and that's not going to help. But what I want you to do is, like, when you are doing a question or when you are trying to solve a problem, please look into the appropriate table. If it is compressed liquid, the table says it's compressed liquid. You don't have remember B 1.3 or whatsoever. But as this is an online medium, what I would do is I will open up the PDF of the property table and do a quick search. Like, the shortcut for the search is Control F. I know all of you know that. So Control F, and I'll search compressed liquid or water, something, and then I scroll through until I find the applicable table for my case, right? So please beware that for certain cases, the compressed liquid tables may not be available, right? So compressed liquid tables are not as comprehensive as two-phase region tables. So in that case, sometimes you might need to use that assumption we made. So the assumption we made in a TV diagram, you remember we did this one. The specific volume of a substance is not going to change too much in the compressed liquid region with added pressure. Sorry. Right? So are we clear on that regard? Any questions so far? I guess this one is just the introduction, so you may not have many questions. So let's move on to the next one. Okay. So for compressed liquid, so you see that this is B 1.4. This is an example, right? For compressed liquid, you have a given pressure, and only variable you have is temperature. Why is that? You remember the pressure has minimal impact on the final outcome of the specific volume and other properties in the case of compressed liquid, right? Therefore, we only have one compressed liquid table. For a given pressure, we have the variable temperatures. But if you compare these numbers, let's say you get 20 Celsius and the specific volume here, it's going to be 0.001002, right? And then you go to two-phase region tables, and then you take the saturation temperature 20 Celsius, and then you check VF at 20 Celsius in two-phase regions, two-phase tables. It will give you a very close answer. It will give you a very close answer. Not going to be too far from this number. So this is why, because why? This is due to the same discussion we had earlier. Because in compressed liquid region, the specific volume is not going to change too much with the pressure. And for now, I want you to forget that you see these parameters in the tables until we discuss it, right? Internal energy, enthalpy, and entropy. So we'll be dealing with these parameters soon enough. But for now, just forget that you see it. Just focus on the ones that we discussed, the ones that we have already learned: specific volume, temperature, and pressure. Okay. And then we are moving into the next one, saturated water vapor, right? So this is a table that you will be using pretty often in the calculations, because we'll be dealing a lot with the two-phase region, two-phase mixtures, right? So when it comes to the saturated water tables or saturated ammonia tables, anything, like you can see the temperature and pressure is given, and then we have the values for Vf, Vfg, and Vg, right? So Vf, sorry, oops. Vf is going to be on this line. This is Vf, and for the same temperature, Vg is going to be this guy, and then the difference between this is going to be Vfg, right? So you can get these readings. For water only, you see two tables there: temperature entry, pressure entry. So we call it temperature entry, pressure entry. So why do we have two tables there? So when it comes to temperature entry tables, they go with 5, 10, 15, like 5 Celsius increment. So let's say if you get a question with asking you to find the specific volume uh, of saturated liquid at 10 Celsius. So you just go there, and then what you do is you find the 10 Celsius, 10 Celsius, and then you have the line you are interested in, right? So in this case, if you were to use pressure entry tables, you cannot find 10 Celsius here, right? The 10 Celsius is somewhere in between these two, but it is not given, right? So in this case, if you try to use pressure entry tables, you will have to do some other subsequent calculations, right? So if you have been asked to find the specific volume of saturated liquid at 1 kilopascal, then it's easier to use pressure entry tables because it goes by the pressure, right? 1, 1.5, 2, something like that. So now you pick one, and then it's there. And if you were to try this with temperature entry tables, it will be difficult because you don't have exactly one. You have 0.8 and 1.2, right? So only the bracket. So you'll have to do some subsequent calculations to get into your answer. These two tables are there only for your convenience. Even if you solve using the wrong table, not the wrong table, like I mean using either of these for the same question, then you will get the same answer, but one will take more time to process, right? Okay, so I have a question. These tables are going to be given in the exam, right? Yes, George, it's already uploaded under the important documents. All the tables are there. So if you go there and see, those are there. I highly recommend all of you to download these once we are like doing the questions, right? So are we all clear about this temperature entry and pressure entry situation? About why we have two tables? Anybody having confusions or questions? Or are we all clear? Perfect. If this table is used to find average specific value, is used to find average specific value. So your question is not clear. Average specific volume. So these two tables are to find properties, right? It could be specific volume, it could be internal energy, enthalpy, entropy, whatsoever. Like we have not studied those yet. But the first one, as Thomas said, the first one goes by temperature intervals, and second one goes by pressure intervals, so that it's just for convenience, right? So if you want to find, for whatever reason, if you want to find VF, VFG, or VG value at a given temperature or pressure, then you can use these tables. So one including this one. This one was for compressed liquid. So this one represent a different region compared to what we are discussing right now. So this one is for this region, right? So this table is for this region. So HU and S, it will be there in saturated water tables as well, but like in this image it's not there. Okay, so if you like, once we get into enthalpy, entropy, and internal energy, like we'll discuss how to find that using saturated tables and other tables. Are we clear? Did I answer? Okay, perfect. So now we discussed about the compressed liquid tables and two-phase tables, and now we have superheated vapor for water, right? So this is going to be this region, right? So there's an important observation. So there's a pressure value. So this pressure value is very important in the case of superheated vapor. You remember we had a pressure value similar to this put up on the table in the compressed liquid, but we said it's not very significant. But in compressed or in superheated liquid, superheated vapor region, this is very important. So if you were asked to find, the specific volume of superheated vapor at 10 kilopascal and 100 Celsius. So basically, you browse through the tables and until you find 10 kilopascal, which we already have found, right? 10 kilopascal, and then you note down 100 Celsius, and then you pick whatever the property that you are interested in, right? So specific volume is what we asked for earlier. So now it's here. And if it is 20 kilopascals pressure and 100 Celsius, can we use this table? Can we use this table? If you were asked to find the specific volume of superheated vapor at 20 kilopascal and 100 Celsius, can we use this portion of the table? We cannot, right? Because for gases, the pressure really matters. With pressure, the characteristics really change. Therefore, we cannot assume that, okay, 10 kilopascal is somewhat closer to 20. No, we cannot do that. So we have to find exactly 20 kilopascals and then do the needful, right? So we'll look for 20 kilopascals and then go for say 100 Celsius, then locate our property, right? So like this is for solid vapor region, right? Solid vapor region tables, like similar to other two-phase tables, like there's a table for that. But in this course, we will not need this table for our calculations, right? So similar to this, like this has the specific volume at a given temperature pressure combination for saturated solid, and then saturated vapor, and then the specific volume change during the process, right? But we will not be using this table for in the course, right? So if you want to find triple point parameters for a given substance, it's here as well. But like there are separate tables for triple point parameters as we discussed earlier. Okay. Now to summarize what we did today, so a state of a pure substance is defined by any two independent properties from T, P, X, V, or other three parameters U, H, S. Like these are about to come. Like still you have not studied this one, but up to now we have studied temperature, pressure, quality, and specific volume. And very important to note that two independent parameters, right? Two independent. So in the case of liquid vapor region, if we have temperature and pressure, can we define the state? I'm reiterating this question just to see whether you remember. If we have temperature and pressure, can we identify the state? One answer is no. Anybody? There's another answer saying yes. I believe like Deza is right, because we cannot determine a state inside the dome using temperature and pressure only, because these two are not independent parameter. Inside the dome, for a given temperature, we know the pressure. It's the saturation temperature and pressure. If you remember, even in the tables, like these come in pairs, right? So for given temperature, we have the pressure. For given pressure, we have the temperature. Likewise, right? Therefore, like just knowing those two is not enough, because by knowing those, one of those, we can locate this line, but knowing this line is not enough to locate the point, right? We have to find specific volume or quality or some other independent parameter other than pressure and temperature. Are we clear there? Perfect. So now there are other important observations. If pressure is higher than saturation pressure, it's going to be a compressed liquid, right? So you remember, in the previous case, we draw P, V diagrams, and then isothermal lines like this. So when this is the saturation pressure, right? This is the saturation pressure, P set. And if our pressure is higher than saturation pressure, like it's this region, so it means it's in the compressed liquid region, right? So in a TV diagram, if we draw an isothermal, constant pressure line, so you can see that if our temperature is lower than saturation temperature, this is saturation temperature, right? T set, right? This is saturation temperature. So if it is lower than, if our temperature is lower than the saturation temperature, it's again compressed liquid region. And if our saturation pressure or saturation temperature is the temperature that we have, is the pressure that we have, then it's definitely inside the dome in the two-phase region. if our pressure is less than saturation pressure, from this one you can see that we are in superheated vapor region. So if our temperature is higher than the saturation temperature, we will be in superheated vapor region again. So are we clear about that aspect? So once we get to know these things, like when we receive a problem, we determine, okay, what tables we should use, right? Looking at these numbers, we figure out, okay, this is this, and then we pursue the solution using those tables, right? Are we clear with this part? Anybody having doubts or anything not clear? Anybody having doubts? Perfect. So perfect. So if temperature and X or pressure and X are given, then definitely you know that this is a discussion about two-phase region, right? So we have to look into saturated liquid vapor tables, because X cannot be defined for compressed liquid or superheated regions. So if there's X involved, that means, okay, we have to look into this thing, right? So sometimes the question will ask, calculate the X and see whether this is inside the dome or not. So if you get a value above 1 or below 0 for X, then definitely it doesn't make sense, because X cannot be out of 0 and 1 region. Therefore, in that case, we see that, okay, this is not inside the dome and it is somewhere else, right? And so we can also look into this third notion, looking at specific volume. So if we have been provided with specific volume and our specific volume is less than the saturated liquid specific volume, VF, so then what can we say? So if we draw a dome again, so we have VF here. So for a given temperature or pressure, if our specific volume is less than VF, that means we are in this region, right? Which is the compressed or subcooled liquid region. So for a given situation, if our specific volume is higher than Vg, then it means it is in this region, right? So which essentially means it is in compressed liquid region. For a given situation, if our V is in between these two, Vf and Vg, our specific volume is somewhere here, let's say, at this point, and then we know that it's in two-phase region. Are we the things that we discussed? And in addition to these points, the other important notion that we found today is, if a compressed liquid table is not found, you can assume that V, or internal energy, enthalpy and entropy, that we have not learned yet, but specific volume of a given compressed liquid at a given temperature is similar to the specific volume of saturated liquid at that temperature, Vf. Okay, so that is the theory component that we plan to cover today. So do you have any questions or any doubts? And now it's time for questions. If you have questions from yesterday class as well, like, you can stay. Otherwise, if you don't have questions from yesterday or today, then you can leave, or you can wait for others to ask questions so that you can learn from it. Yes, Kylie, that is a very good question. So all the volumes in these tables are specific volumes. Yes, because the tables are presented for only for intensive properties. If we use extensive properties, then it will be subjective for different systems, right? Therefore, we only use intensive properties. Yes, therefore, the volumes that we have in these graphs are specific volumes. Will P and P set will be provided. So Menna, like depending on the question, you will be provided with the pressure or specific volume or any other parameter. So you can determine, if you know the temperature, then you can determine the P set. So if you know the temperature, then you can determine the T set, right? So likewise, you have to use the property tables to find P set if needed. No, Kylie, you are getting it perfectly right. I mean, if we don't have the intermediate values, we are going to use interpolation. So we'll refresh our memory on linear interpolation in the coming lectures as well. So yes, we are assuming a linear relationship and we are doing linear interpolation. Yes.